Good morning, Professor and fellow lab members. Today, I would like to present a paper that is related to the previous draft that we made regarding the pseudo-labeling. And this paper is titled Deep Metric Learning-Based Pseudo-Labeling Framework for Class Imbalance Semi-Supervised Learning. And this is the content for today's presentation from introduction up until the conclusion. So, as we know from many previous works background, in the real world, there is an imbalance of samples quantity between all available classes with different amount of unlabeled data. And this problem is later addressed as the class imbalance problem. And according to many previous works, it can happen due to budget, human resource, or planning allocation to label the data. However, existing algorithms are mostly supervised learning, or it only utilizes the labeled data and cannot learn from the unlabeled data. So another direction is to pursue semi-supervised learning that can utilize both data. However, most of the previous work assumes balanced class distribution, and practically class imbalance and insufficient labeled data are two problems that often exist together. And it is a challenging issue to tackle both problems for semi-supervised learning. So those problems cause the SSL model to be biased towards majority classes that have numerous samples and against minority classes that have fewer samples. So the existing work often handle the class imbalance and insufficient labeled separately. For example, there are many resampling methods that try to balance the labeled data quantity, but it doesn't address the imbalanced unlabeled data. And also some works try to handle the problem simultaneously by either refining biased pseudolabels during the semi-supervised training. For example, another previous work, imbalance, try to introduce an imbalance parameter and then a sampling rate to select more pseudo-label belonging to the minority classes. And then also some works try to modify the loss function to enhance the discriminative power for minority classes, but they are still affected by the biased pseudo-labels. And recently, there are many works on representation learning, or in this case, deep metric learning, that try to improve the pseudo-label generation. In this case, it tries to optimize the feature representation and then the decision boundary. And to tackle both of those problems, this work proposed deep metric learning based pseudo-labeling that can optimize the feature representation of the labeled and also the unlabeled data by increasing the interclass segregation and intraclass compactness. And these are the list of the previous works related to this work. First is the basic pseudo-labeling that takes the class with the largest predicted probability to generate the pseudo-label, and then mean teacher, where it performs consistency regularization between the prediction of ensemble models for assigning the pseudo-label. And then this is also mentioned by Tori last time, mix match. It performs the pseudo-labeling and consistency regularization on mix-up augmented training data. And also the advanced version is fixed match. It performs the weak and strong augmentation strategies on unlabeled data. And the another variation is remix match, which is just an enhanced version of mix match with augmentation, anchoring, and distribution alignment. And another work, LDAM, it is a deep metric learning method with a modified loss function based on the label distribution aware margin. And then another work, CRT, it is a rebalancing method for class imbalance supervised learning that retrains the classifier with class balance sampling. So in this paper, there are three main components. First is the deep metric learning, as we can see in here, and then the pseudo-labeling, and then the network fine-tuning. First, the deep metric learning learns the compact and improved feature representation of the data, and then the pseudo-labeling tries to find the center of features representation for label data through the clustering, and then generates the pseudo-label. And then network fine-tuning tries to fine-tune the trained network to generate better pseudo-labels. So for the first component, these are the steps. First, we need to sort the labeled class in terms of quantity. So N1 will be the biggest data and NK will be the smallest class with smallest data. And then try to build set of intra-class and inter-class set. So the intra-class set in here, it has pair of data with same label. And then the inter-class set have pair of data with different label. And then we try to perform the forward operation of the neural network and then calculate the pairwise distance. And this is how we calculate the loss. So we try to encourage the intra-class samples to be closer, or we try to pull them together. And then for the inter-class or class with or pair of samples with different class, we try to push them apart. And then this is the parameter alpha, which is the margin for enforcing the enforce between the similar and dissimilar pairs. And then this is the result of the training that we hope. So before it is for the intra-class, it is separated. For the inter-class is also some kind of close, but in the end, we want the intra-class to be clustered together and for the inter-class to be separated apart. And for calculating the total loss, this is the total loss. So this is the pull and push loss, and then there are some trade-off parameter that we can introduce. And also this is just regularization term for the loss. And then the second component is pseudo-labeling. So for pseudo-labeling, first we calculate the output or forward output of the labeled data and unlabeled data. And then we perform the clustering on the labeled data representation to find the feature centers of those clusters. And then to assign the pseudo-label for each unlabeled data, we try to find the cluster with minimal distance, with the most minimal distance with the unlabeled data. And then if we find it, then the cluster with minimal distance with the unlabeled data becomes the label. And then for the network fine-tuning, basically there are two minor components. First is the classification loss. So instead of using the general cross entropy loss, they modified the loss with calculate the weighting parameter. So this is how they calculate the weighting parameter. And IRT is the imbalance ratio between the at the t epochs. And for the IR, actually how we calculate it is to find the class with the biggest sample divided by the class with the smallest sample, the NK. And then we calculate the modified cross entropy loss. And then there is a parameter for the scaling factor of easily classified samples. And this is the definition of the easily classified samples, which are samples that have a high probability to be classified correctly in majority classes. And then the second component is distribution alignment loss. So class imbalance in the unlabeled data may cause minority class distribution to be challenging to align when the majority class dominates in the unlabeled data. So to ensure that the labeled data and pseudo-labeled data follow the same imbalanced class distribution, the author designed this distributed alignment loss. So for pseudo-labeled data, we try to first calculate the labeler divergence with the original labeled samples. And then we try to split the pseudo-labeled data set into intra-class set and inter-class set, like we see in the previous slide. And then we calculate the alignment loss in here. So this loss try to maximize the distribution discrepancy between the inter-class data, and then minimize the distribution discrepancy between the intra-class data. And C1 and C2 are trade-off parameter in this loss. And so this is the total objective function for the network fine-tuning. And KTSSL is the weighting parameter that varies according to the number of training epoch because it is updated as in here. And as the training process progresses, the goal of this component is to gradually shift from distribution alignment to classification optimization. Therefore, the learned network can expand the decision boundary around the minority samples. And this is how they split the data for the experiment setting. So they use this imbalance ratio or IR and also labeled ratio or LR for the settings. And then they try this data set CFAR10 and CFAR100 and also ImageNet 127, which is a modification from ImageNet, original ImageNet. And we can see the settings as below in here. And for the evaluation metrics, they use balance accuracy, which is just the half of the total recall plus the specificity. And this is the environment and hyperparameters they use for the training. So actually for this one, I'm not sure how many epochs available in here. So maybe this is specific to the TensorFlow because they say they train it for 6 rounds with 2 power by 16 steps. And this is the result for the first data set. So in performance of all methods actually decrease when the imbalance ratio increase, and then the performance increase when the labeled sample ratio increase. And all of these methods achieve the best when IR is set to 50 and LR is set to 0.3. And then for the SSL methods, such as fixed match and remix match, it outperformed the class imbalance supervised learning, such as the resampling, LDIM, and CRT. And according to this result, fixed match generally achieved the best performance among all SSL models. And using the proposed work, it outperformed fixed match plus some modification LA by 1.2% in terms of balance accuracy. And also the proposed work outperformed the current CI-SSL models fixed match plus DARP and fixed match plus CRAST by 3.5 and 1.4% respectively. And the author also put the normalized confusion metric to evaluate whether the classifier successfully detect all training samples of the K class. So in here we can see that the proposed framework achieved the best performance on the minority classes. However, there is also some low performance on another minority class, but the author did not address it in the paper. And all the CI-SSL baseline models rebalance the bias pseudo-labeled data through resampling or reweighting strategies, which rely heavily on the quality of the generated pseudo-labels, as we see in the background. In contrast, the proposed method generates more accurate pseudo-label by optimizing the feature space of labeled and unlabeled data. And therefore, in here, we can see that the proposed DML-PL can achieve a better performance than fixed match plus LA and fixed match plus DARP and fixed match plus CRAST. So, like I said before, I'm not sure about the way they calculate the round. So in here, from the table, from the graph, it seems that one round of training equals to 60 epochs because for the settings, they set the training to only one round. So you can see as the number of training epochs increase, pseudo-labeled data are gradually incorporated into the original unlabeled data. However, for this graph, I'm not sure how to interpret this graph correctly. And for the class distribution of each class changes accordingly, resulting in gradual change in the imbalance ratio and also the weighting parameters, as we can see in the table. And for the loss, as the loss drops, the performance improves accordingly, like we can see in this figure. This is because the dynamic imbalance ratio, IRT, and the weighting parameters can help the model to pay more attention to the minority classes. And then this is another result on large classification dataset. So in here, CFAR 100 contains 100 class with the biggest number of sample for a class is 500 samples. So it is harder to learn from this dataset. And from the result, all models achieve their best performance when IR is set to 10 and labeled ratio set to 0.3. And the DML-PL outperforms fixed match plus DARP by 1.2%. So the reason why the proposed method works, when the imbalance ratio is set to 10, 20, and 50, the least minority class has only like 15, 8, and 3 label samples respectively. And this makes it difficult for other baseline to determine the appropriate resampling or reweighting ratio. But in contrast, the proposed framework exhibits relatively robust performance as it is independent of the number of labeled samples and generates pseudo-label for unlabeled data by nearest neighbor selection. And then another result on the large classification dataset, the proposed framework outperformed the fixed match for this LR setting by 3.4%, 4.2%, and 1.4%. And it also outperformed the other previous work. And this shows that the DML-PL framework achieves a superior performance when dealing with large-scale dataset. And the author tried to see the effect of each component. So first, if the deep metric learning is replaced with standard cross entropy, we can see that the performance decreased by 5.3%, 7.6%, and 8.8%. So deep metric learning optimized the feature representation, like I mentioned, by increasing the interclass segregation and intraclass compactness. Therefore, it supports more reliable prediction for the unlabeled data. While for the pseudo-labeling, the author tried to replace the pseudo-labeling with general confidence threshold, like in the pseudo-labeling, and then the performance dropped by 4.2%, 5.1%, and 6.7%. So the proposed pseudo-labeling explored the relationship between the labeled and unlabeled data rather than the confidence threshold for class probability, which result in better prediction for the minority class. And then for the network fine-tuning, so we can see that without the fine-tuning, the performance dropped by 1.9%, 4.2%, and 4.5%. So the network fine-tuning can help to refine the performance. So according to the paper, the loss function CL and DAL ensure the classification performance and distribution alignment of the unlabeled data. And then the author tried to see the sensitiveness of the previous deep metric learning parameter margin alpha. So as a reminder, the margin alpha defines the control of the interclass segregation and the intraclass compactness in the deep metric space. So we can see in here, the performance starts to degrade rapidly when alpha is set to be larger than 10. So from this result, we can see that excessively large margin will cause overlapping between classes, which lead to performance degradation, and then excessively small margin cannot sufficiently separate samples from different classes, and therefore also decrease. So based on this experiment, the value of alpha is optimal at 0.1, 0.5, and 1.0. And this is the conclusion of this paper. So we can see that class imbalance and insufficient label data often exist together in practical real-world application. However, most previous work tried to tackle those two problems separately instead of together, resulting in the model bias towards the majority classes. And this work tried to handle the problem simultaneously for class imbalance semi-supervised learning. Deep metric component tried to learn compact feature representation for labeled and unlabeled data, while the pseudo-labeling tried to generate reliable pseudo-labels for unlabeled data, and then the network fine-tuning tunes the deep metric learning for generating reliable pseudo-label in the training. And the performance result on the listed benchmark show that the proposed DML-PL outperformed the baseline and achieved a state-of-the-art performance. This is the reference that I use for my slide. Thank you for listening to my presentation.